Everyone, in this video we're going to look at and probabilities, which are calculated using the multiplication rule. So here's what the multiplication rule looks like. I wrote down 3 different versions. This is finding the probability of A and B, or sometimes we would write this as the probability of A intersection B. These are really the same thing, just different notations for 2 events both happening. And this is calculated with the probability of A times the probability of B given A. And you could also do this in the other order. There's nothing special about A and B. You could do probability of B times probability of A given B. It doesn't matter the order. So in the video about independent events, I mentioned that independence is important when we talk about using the multiplication rule. So if A and B are independent, then this second probability here, probability of B given A, if these are independent events, then the given A portion doesn't really matter. Probability of B given A is exactly the same as just the probability of B. So if I restate our multiplication rule, we get that the probability of A and B, or the probability of A intersect B, is just the product of the probability of A and the probability of B. So you could write these down as 2 different rules, one kind of the general multiplication rule, and then one specifically for independent events. But I would recommend really just doing one rule because you can always use this general rule. And if A and B are independent, then the conditional portion of the probability just won't matter. So here's an example. If we randomly select 2 people from a class of 30 people, what is the probability that both were born on a Monday? This is an and probability, but it's not super obvious because the statement of the problem doesn't actually say and. The and is sort of encoded in this term both. So when we say that both people were born on the Monday, you can think of this as the first person was born on a Monday and the second person was born on a Monday. So whenever you have multiple events that are all happening, in this case, 2 events that both happen, you want to break them down as one event and then another event, in this case with an and. So I'm going to apply my multiplication rule here. This is going to be the probability of my first event, the first person born on a Monday, times the probability of the second event given the first event. So I've written this out in words or probability notation here. I have probability that the first person was born on Monday times probability the second person was born on a Monday given that the first person was born on a Monday. Now, if I think about calculating these probabilities, particularly the second one, this condition, the given that the first person we select is born on a Monday, if we know the first person was born on a Monday, does that have any effect on whether or not the second person is born on a Monday? In this case, it shouldn't, because the days people were born on are independent. It doesn't make any difference if your classmate was born on a certain day. That's not going to affect the probability that you were born on a certain day. So the second probability, the conditional probability, is really just the probability that the second person was born on a Monday. And that's because these are independent events. So the condition just doesn't really matter. So really, this is just the probability of each of the people being born on a Monday multiplied together. The probability that anyone is born on a Monday is just the number of possible days there are, or well, Monday out of the number of possible days you could be born on, which is 7. So this is 1 out of 7 times 1 out of 7. And if I multiply those together, I get 1 out of 49. That would be the probability that selecting 2 people from our class, both were born on a Monday. Notice that the size of the class doesn't really matter here. I'm not looking at the proportion of people out of the total in the class. I'm just looking at the probability of the day of birth for each person. Here's another example where the events are actually dependent instead of independent. So the scenario here is that there's a sobriety checkpoint, 574 drivers are screened, and 7 of them are arrested for driving while intoxicated. So if we randomly select 3 drivers from this group without replacement, what is the probability that all 3 were not intoxicated? So again, this is an and probability, but it is sort of in disguise. I want to think about, I'm finding the probability that all 3 drivers were not intoxicated. This is really 3 different events. This is the first driver was not intoxicated, and the second driver was not intoxicated, and the third driver is not intoxicated. I don't want to write all that out, but I'm just going to write here probability first not intoxicated, I'm abbreviating this NI, and second not intoxicated, and third not intoxicated. This is an and probability. We actually have 3 events here instead of just 2, but the multiplication rule still works. We're just going to kind of extend it. So I'm going to start with the probability of the first event. So probability that the first person we select was not intoxicated times probability that the second person was not intoxicated, but this is given that the first event has already happened. So given that the first person was not intoxicated times probability that the third person was not intoxicated, given, and in this case, we're assuming that both of the prior events already happened. So this is the first and second people were both not intoxicated. So this is what that kind of extended multiplication rule would look like. It's a product of 3 probabilities where we kind of add the conditions of the initial events as we go down the list. So like the last example, I want to think about, do these conditions that the first person or the first 2 people were not intoxicated, does that make any difference to the next person being intoxicated or not? And in this case, it does make a difference because these 3 people are being selected without replacement from the group of drivers. So if the first person was not intoxicated, and we sort of removed them from the group, then when I go to select the second person, the probability that they're not intoxicated is going to be a little bit different, and we have to adjust for that. So I'm going to start here with the first event. If I just select one person from this group, what is the probability that they're not intoxicated? Well, I know that the total number of possibilities, the total number of drivers I could select is 574, because that's the total number of drivers available. The other number I'm given here is 7, but the 7 is the number of people who were intoxicated. So I need to actually figure out how many of the drivers were not. So that would be 574 minus 7, which is 567. These were the people not intoxicated. So the probability of the first driver I select not being intoxicated is 567 out of 574. That's my first probability. Times. Now I look at, okay, what's the probability that the second driver is not intoxicated given that the first driver was not intoxicated? Because I'm selecting without replacement, I have fewer possible drivers. There's 1 fewer driver in the entire pool. So my denominator is now 573. And because the first person was not intoxicated, then the number of non-intoxicated drivers is also 1 less. So this is 566 times, keep going down the line, the third person not intoxicated. I've now removed 2 people from the pool, so there are only 572 left. That's my denominator. And the numerator is going to be the number of non-intoxicated people left, which would be 565. And I'm going to put this all in a calculator to see, what does this calculate out to? As a fraction, it's going to be a super big number over a super big number. So in these cases, we probably would state our probability as a decimal. And for this probability, I get 0.963 8 if I round to 4 decimal places. Or we could think of this as about 96%. So there's about a 96% percent chance that if you randomly selected 3 people from this group of drivers, that all 3 of them were driving sober. I've got one more example I want to look at. This one is a little bit more of a real life example. So government authorities at NOAA are inspecting a sample of 3 seafood portions from a large shipment to test for safety. So we have a large amount of seafood coming in. They can't test everything, so they randomly select 3 portions and test them for things like contamination or temperature and things like that. So I'm going to look at a shipment that contains 2,739 portions of seafood. And I'm assuming that we know about this shipment that 247 of those portions do not meet the safety requirements. So we have sort of knowledge about the makeup of this shipment. And the question here is, given those proportions, what is the probability that all 3 portions that are tested are good and that this lot is accepted in for sale? So this is similar to the last problem. We're looking at 3 tests, and we want to know what's the probability that all 3 are good. I'm just going to kind of write down the relevant information here so we can have a little bit more space to work. So there were a total of 2,739 portions of seafood, and 247 of those were bad. They failed the safety criteria in some way. And the probability that I'm trying to find is that all 3 selected are good. The probability that all 3 selected are good really means this is the probability that the first is good, and the second is good, and the third is good. So all 3 good really is an and probability. We're looking at 3 different events all happening. So I'm going to take that and probability and I'm going to apply the multiplication rule just like we did in the last example. So I'm going to start with the probability that the first piece of seafood was good times the probability the second was good given that the first was good times the probability the third was good given that given that the first and the second were good. So we have these conditions of the initial each event happening as the next one happens. Now, just like with the driver's example, I need to think about, is the probability going to be different based on these conditions? So when I look at the probability that the second piece of seafood is good, given that the first is good, does that matter? And this really all comes down to, are we selecting with or without replacement? So if this is with replacement, then these events are all independent and I don't need to consider the conditions here. I just do probability first is good times probability second is good times probability third is good. If this is without replacement, then these are dependent events because by not replacing each portion of seafood, I'm affecting these numbers here. I'm affecting kind of what is in the pool, what's available for testing. In most cases, sampling is done without replacement. If you think about if NOAA is going to select portions of seafood, they're likely not going to select one, test it, and then put it back into the pool and somehow randomly select it again and potentially test the same piece twice. That's just not likely how they're doing it. So this is probably done without replacement, meaning that these are dependent events. So what this looks like is we are going to have to adjust the probability given that, the first was already removed or the first 2 were already removed. So I'm going to start first with the probability of the first being good. That's my first event here. This needs to be the number of pieces of seafood that are good out of the total. I know the total is 2,739. But I need to figure out how many of them are good because I was just given how many were bad. This is very similar to the driver's example. So I'm going to take my total, 2,739, subtract the 247 that were bad, and that gives me 2,492 pieces of seafood that are good, that meet the safety requirements. So that is going to be my numerator. My first fraction, my first probability is 2492 out of 2739. Now, when I go to the second piece and I want to know, same thing, is this good? If I'm assuming that the first piece of seafood was good and it's been removed from the pool, that means that the total is now one smaller, 2738, and the number of good pieces is also one smaller. The number of bad pieces has not changed, but that's not really part of my calculation here. Times, and then I do the same thing for the third one. If I've removed one extra, that I've taken out the first two pieces for sampling, then the probability that the third is good would be 2490 out of 2737. So a similar calculation to the last one. I'm assuming that these are dependent events, that these selections are made without replacement. In this case, if you calculate this out, it comes out to about 0.7530. Now I want to consider the same setup, but assume that these are independent events. So maybe we're assuming that these are selected with replacement. The calculation is going to be similar here, but when I look at each probability, the probability that the first is good and the second and the third, these probabilities are all exactly the same. These are all going to be the total number of good, 2492, out of 2739. I'm going to have that number times itself, and then times itself again, which we could write in shorthand as the 2492 out of 2739, this fraction cubed, or raised to the third power. It's the same fraction times itself, a total of 3 factors, 3 times. This is easier to calculate on a calculator because they're all the same number, and this comes out to 0.7531. Now, I'm sure you all memorized the answer from the previous slide. The previous calculation where we said that they were dependent, the answer was 0.7530. So these are almost exactly the same, and that's because when we select a small number of, in this case, pieces of seafood out of a very large total, the amount that these probabilities change is so small that we likely don't really even need to account for it. So when I'm thinking about the multiplication rule and I have this sort of general case and the independent case, there are some examples where we can treat events as being independent even though they're not really independent, just because the change between the conditional probability versus the non-conditional probability is so slight that it doesn't really make a difference. Now, if I come back to the seafood example, note that there is a fairly significant portion of bad seafood here. The 247 out of 2739 is about 10%. And there's a pretty good chance, about 75% chance, that this shipment would be accepted. So a question that we should be asking is sort of, is this testing method sufficient, right? There's about a 25% chance that we would catch the bad seafood here, but 75% of the time it's just going to go through and all of the seafood is going to be sold. If we're okay with that, then that might be an okay solution, but we might consider, all right, I want to have a better confidence level of finding this shipment as, not good. And one way you could do this is to select more samples. So rather than just doing 3, what if we did 15? Now this is still an and probability. The probability that all 15 are good would be the probability that the first is good and the second is good and the third is good and the fourth is good, and so on and so on and so on. In this case, it would be a huge pain to do the dependent calculation because you would have individual probabilities that were all slightly different for 15 different selections. It would still be a multiplication rule, but this would be a big pain to compute. Now, you could compute it, and especially using technology, it's not a huge deal, but Because we know that this sampling is from such a large pool, we likely would just assume that these are independent or treat them as independent. And then we could say the probability that all 15 are good is just the probability that any one of them is good raised to the 15th power. We're multiplying that probability the first is good times probability the second is good times probability the third is good, etc., assuming that these probabilities are all going to be the same. This would be 2492 out of 2739 to the 15th power. So if we actually did 15 samples, the probability that they were all good is actually only 0.2423. So we've drastically reduced the likelihood that the shipment would be accepted, and this might represent a better method for checking. That's it for this video. Thank you for watching.